Hey everyone, how are we doing? Mulebot is out again. Ay, 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 ay. It is the hassle of it works sometimes and it doesn't work. I'm over here on the main screen. And I go to Mulebot and I say, hey, how you doing, Mulebot? Run as admin. He says, I'm doing great. How about you? And then it comes up over here and says, nope, not happening. And then I say, but I want that. I go here. Yes, you can make changes. I go here and I say allow on device. It says, okay, you're allowing it. Learn more. Sure. This is what they told me to do. How's it going, Noel? Good to see you. Run as admin. We'll do, I mean, we're going to say he can go through again. It's just me every time I try to run Mulebot. Well, he's on vacation again. He came by yesterday for a little bit. Well, Mulebot's on vacation again. That's the way it goes sometimes. He comes by, he says hey, and then he says I'm out again. We missed him yesterday, or we said hello to him. And he said goodbye to us. Sad day. So with that, we can get started on some work right here. Let's take a look at what we got coming up right here, because we have chapter 10. We also have a Canvas content right now. It's actually on 10 and 12, so maybe we'll do some chapter 12. So this is where people get stuck, and let's put it in the notes right here, Canvas content. Canvas content. That's an old office hours. That's probably why I can't edit it. Sounds good. Let's get the Canvas content done right here. Let's go get the Canvas content. That's why I can't edit it. Edit video. And now let's go right to edit and let's go do it. Okay, here we are. Canvas content. Canvas content number 6. Gonna get it done. And this is at the 5:33 mark. So this is Stat 201, Canvas content number 6, chapter 10 and 12. So once again, we're going to review the concepts here, but see if you can get them. The sampling frame is the list of all possible outcomes. Is that the sampling frame? The sampling frame is the list of all possible outcomes. True or false? What do you say? See if you can get this without me. You should have definitions for this. Sampling frame. The sampling frame, is that the list of all possible outcomes? True or false? Don't worry about being wrong. Just take a guess. The sampling frame. It is actually false. I wish Mulebot was here to get, we'll hit the points button. It's actually false. And let's take a look. And don't worry, this is time to review. The sampling frame are all individuals or things that we could sample from. So the sample frame is the list of individuals or things we can draw from, where the sample space is the list of all possible outcomes. So make sure to have some flashcards right here with the sample space is the list of all possible outcomes. So a sample space looks like when you have heads and tails of a coin, this would be a sample space right here of the coins of all possible outcomes. So this is a sample space on the screen of when you flip a coin 4 times, versus a sample frame would be the people you could sample. So we talk about something, suppose that we only collect samples from population members that are convenient. That's not really good for that. Here we go. You go to the UT dorms and select 2 floors. What would be the sample frame right here? So you select 2 floors from every dorm. So what would be the sample frame? So the sample frame would be what? See if you can figure out the sample frame for this. So we'll say, what is the sample frame? So the sample frame is everyone you could have theoretically sampled. So you go to the UT dorms and select 2 floors from each of the dorms. The sample frame is defined as everyone you could possibly sample. So the population is everyone you're interested in. The sample frame is everyone you could possibly sample. And then the sample is the people you get data on. To repeat, the population is all individuals we are interested in. Kind of. The students on the floor are going to be the sample. Every student in the dorm is the sample frame because the sample frame is theoretical. We could have talked to anybody in the dorms. If we take random floors, well, then we could have took any floor. So any student who lives in the dorm is in the sample frame, which could actually be the size of the population. Maybe we're interested in students who live in the dorms, so we go to the dorms and speak to random floors. Now, any student who lives in the dorm is a student we could possibly speak to. Everyone you have access to, exactly. So it's not everyone you talk to, because that's your sample. The sample frame is everyone you have access to sample. So the sample frame will be every individual you have access to sample. It's not the sample, because the sample is everyone you get data on, and the population is everyone you're interested in. It usually goes down in this order. I don't like sampling design in there. It usually goes down in order of population's the largest. Sample frame could be the next largest. The text on this, that's better. It's not really good. We shouldn't have put white text on yellow. I should talk to Terry about that. That is not very good. That's not. Try thing out there. That's better-ish. Yeah, I don't know why it's white text. There we go. So there it is right there. Entire group of individuals or things. All this right here is what the population, sample frame, and sample are. Make sure to have definitions of those. Make sure to be able to do examples of them. So the sample frame would be all individuals we have access to samples. So this is false. This is a definition of the sample space. The sample space is a list of all possible outcomes, which is like if you flip a coin 4 times, this would be the sample space of flipping a coin 4 times. That is what a sample space is. The sample space is the list of all possible outcomes. So good review of that topic. We got it. A researcher wants to examine the grams of milk and fat. They separate it into 2 groups or multiple groups. They randomly select cartons from each group to measure the fat. So now they're separating it into groups, and they're taking cartons, and they're just taking a sample from the carton. So the carton is just the sample itself. It's not a whole bunch at once, if you get my hint. And so they're making sure they get a certain percentage of whole milk, a certain percentage of 2%, 2% fat, and low fat. So they're acknowledging a difference right here. What sampling method is this? They're acknowledging a difference between this and taking cartons from each group. That way they don't undercover a certain group. What kind of sampling method would this be where they acknowledge a difference? It is stratified. I wish Mubot was here. You're 100% right. Stratifying is acknowledging a difference and then sampling in accordance to that difference. And then cluster is when you take a whole bunch at once. Like we talk about taking a box of donuts is a cluster of donuts, and you do a census. So cluster is going to have the keyword census, and it might not say census, but that means to take all of a group. Simple random sample, everything has an equal and likely chance of being selected, like when you have the machine with the balls and you select a random ball. Systematic is every kth observation, and usually you give everything numbers, like enumerate and then select randomly. It's like if you take 10 random students from a list of students, that'd be a simple random sample. If you take every 20th student who walks into the university center, that's a systematic. Stratified is if you go and try to talk to 30 off-campus students and 70 on-campus students. And cluster is if you were to go to classrooms and talk to classrooms of students. So this is going to be here stratified. We have a sample space now. If somebody is having boys and girls, what is the sample space of them having 2 children? So what is the sample space of 2 children? Is it A, B, C, or D? So you have to think of all possible outcomes, and this is also with respect to order. What is the sample space of all children? A, B, C, or D? What is the sample space of all possible children? Like if they have 2 kids and you've got boys and girls, what is the sample space? So you have to think what could occur. We also talk about the probability of the sample space. It's equal to 1. So what's the sample space? What is that which could occur? It is D. There you go. There you go. It takes into respect order. My family is, I guess that's the oldest. There we go. I'm the middle child. That's me. There's Brian with a B. And so that is the sample space, everything that could occur. In probability, the value of each trial is called a consequent. It's called an outcome. This is false. The consequence, we don't even call anything that. But you have the value of each trial is called an outcome, which is on the screen now. And so you have a trial, which is when you flip a coin. Yeah, 2 kids, exactly, 2 kids. The other one I think was 3 kids. So you are correct. That is the sample space of 3 kids. This is the sample space of 2 kids. Actually, really good, Noel. This is the sample space of 1 kid. This is the sample space of 3 kids, sample space of 2 kids. This one doesn't take into respect the order of oldest and youngest of boy and girl. And you have, when you flip the coin, that's a trial. You're doing a trial of flipping a coin. The outcome is when it lands. An event is like getting 3 heads in a row, and then the sample space is the everything that could occur. So down here, we have in this picture the event of 4 heads, and that's out of the sample space of everything that could occur when you flip a coin 4 times. And the probability of this is 1/16. So that is how we can figure out some probabilities. So suppose event A is taking 15 or more minutes to walk to campus and to go to work, and event B is taking less than 15 minutes. Are these 2 events complements, true or false? We have to know what a complement is. So what do you think, true or false? And then let's discuss what a complement is. True or false? What do you think? You have to know what a complement is. It is true, because a complement is everything but that event. So if you were to say the complement of making an A, it would be not making an A. If you say the complement of taking 15 or more minutes to get to work, it'd be taking less than 15 minutes, because either it'll take you 15 or more, or it'll take you less than 15 minutes. And we will assume you get to work. I guess it took you less than 15 minutes if you didn't get to work, because it took you 0 to get to work because you never got to work. It's kind of missing data at that point. But this is true. Complement means everything but that event. And so if you go over here to the notes, you will see the formula for complement is 1 minus the event. So if you go to the complement rule right here, you will see the complement rule. It can also be found, that's addition. And complement rule is going to be right here. And the complement rule, so that we are talking about the same topic, just the 2 and kind of, not really the 2, I guess you could call it the 2 ends, but it's like everything that could occur. Because if you go to the pet store, you could get a dog, or you could get a bunny, or you could get a cat, that's all they have, or you could get nothing. So you could list probabilities, like if they only have this at the pet store, this is everything that could occur. Like you will either leave the pet store if your parents say you can get 1 pet with a dog, with a bunny, with a cat, or a nothing, and the probability of a dog is 40%. What is the complement of getting a dog? Well, the complement of getting a dog would be these things here, and they must have an associated probability of 60%. And that's total probability if you add up the probabilities of these things. And this also assumes that they're disjoint, that you're not going to get a dog and a bunny. Other things that are disjoint are like football games where a team either wins, loses, or ties. And if you have these events right here, your favorite team might have a 60% probability of win, a 38% probability of lose, and a 2% probability of tie. So what is the probability they do not tie? So this would be an example of a complement. What is the probability they do not tie? So there's the probability of tie. So the complement is just doing 1 minus that. So what's the probability they do not tie? Which can also be found right here. Yep. And you can do it by doing 98% by adding up the others, but it's easier if you just do 1 minus. So you can just say, well, let's just do 1 minus this right here, plug it into this equation, and you get the probability of tying is 2%. The probability of not tying is 98%. So that is what the complement is. It's 1 minus the event, and a complement is everything but that event. A complement cannot overlap, and it must include everything. So if you think either Brian drinks coffee this morning or he does not drink coffee, the easiest way to do complements is to say not. Got that down to nice. We'll do one more version here. A lot of good review. The purpose of a statistic is to have enough data to adequately describe the sample statistics. True or false? The purpose of a statistic is to have enough data to adequately describe a sample statistic. What did you determine was A again? Oh, so A is just a substitute for the, like, when you say A, it's like the probability of tying. A is just a substitute for whatever you're saying. So A is just like a placeholder, like the probability of tying or the probability of Brian drinking coffee. So it's just a placeholder, and you would say like the probability Brian drinks coffee in the morning is 90%. What's the probability he does not drink coffee? So it'd be 1 minus probability of Brian drinking coffee. It's just the A is a placeholder for whatever you're talking about. And so you'd have the probability of the complement right there. Does that make sense what complements are? You would say the probability Brian drinks coffee, P of A, or P of coffee, whatever the topic is. So the A, great job, Noel, right there, and good questions. The A is just a placeholder for whatever we're talking about. and then you can do 1 minus that to get the complement. So it's just and really good questions. It's just a placeholder. You just insert whatever you're talking about there, and it's not like you don't do P times coffee. It's a full, like, this is equal to that. It's a description of, like, the probability of drinking coffee is 90%. So you almost read it as a sentence. Math is weird sometimes. Is the point of statistics from samples, is the point of it to describe, is the point of a statistic to describe the sample statistic? True or false? What do you think? Is the point of a sample to describe sample statistics? We call it inferential statistics for a reason. It's actually false. Good guess. The point of a sample is to make inferences into a population. So the point of a sample is to better understand the population of interest. So we call it, like, the population of interest. And we do want to understand statistics. Like, yes, we want to know statistics, but the point of a statistic is to understand the population of interest. So this one's false. We do statistics to understand populations. We will, of course, understand the statistic too, but the point of the statistics is to understand the population. Response bias is always possible in a survey that requires an answer from a human. Response bias is when the surveyor or the question interjects bias into it. What do you think, true or false? So response bias is always possible in a survey that requires an answer from a human being. What do you think? And good answers. Good practice, good answers. We'll do one more version of this. We'll see if we can get as many questions as we can. Very, very true. Very true. Response bias is when I ask you something like, do you think it's fair that a 16-year-old can drive a car but they can't vote? Do you think it's fair that a 16-year-old hasn't had civics classes and they can vote? See, the first one pushes you towards yes, like, or no, it's not fair. You'd be like, you would word it this way. You'd say, since a 16-year-old can drive a car in most states, is it reasonable to allow 16-year-olds to vote? You'd be like, yeah. And then you might say, since 16-year-olds in most states haven't had a civics class, is it fair for should 16-year-olds be able to vote? And you're like, no, I don't think so. And that's usually where we get response bias, is when the researcher or the questions themselves or something well, good to see you. I thought it said DDR for a moment there. I thought we were doing some Dance Dance Revolution. Thank you for being here. And if you want to learn some stats, we're doing stats. I think that depends on who you're asking. Exactly. And then you have what are called lurking variables, because age is going to confound what people think. Because I'll tell you this much, as you get older, which I sadly have done, you start to change your views on stuff. Like, you start to be like, well, when I was 18, I thought this. But now that I'm old, I think this. And you're like, man, I wish I still thought like I was 18. I wish I could have my 18-year-old mindset. But maybe for good or for ill, you start to change your views. And hopefully it's due to information that helps you learn. We got the sample frame right here, which we covered earlier. So check out the earlier version. We talked about the sample frame of children would be boy, 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 girl, girl, boy, girl, girl. With the sample frame of 1 kid, with the sample frame of 3 kids, it'd get really complicated if you talked about 4 kids, but the sample space, and I accidentally said sample frame, but the sample space is everything that can occur. So here's the sample space of flipping a coin 4 times. So you can see all heads, all tails, and all permutations within of heads and tails combos. So sample space, everything that can occur, combinations of outcomes. Here's a tricky one. Now we're going to do some math. So I'm going to call you Dance Dance Revolution. Or I don't know how to say it properly. Default. I will call you by default. Let's go over here and let's bring up. We've had visitors from all around the world sometimes. Here we are with the law of large numbers casino. With the law of large numbers casino, we've got that you pull one of those slot machines right there and you are trying to get a win. And on the machine, it's got these, you ever see these, Noel? You ever see these wheels that you pull the handle? We do a lot of great drawings here. You go, and you try to get it spins here, and on the wheels, they spin and then they show up. And you get so excited because you get an orange and orange and orange. Like, so what we have on this wheel is that each one of these wheels has 4 skulls, 3 lemons, 2 cherries, and 1 bell. That's a orange cherry. And so with this right here, what is the probability that you get a lemon and then a cherry and then a bell? So you get a lemon. Actually, I've got colors for these that'll work. A lemon, and then a cherry, and then a bell. Best bell ever. Oh, okay, that works. That works. You get a lemon, and then a cherry, and then a bell on this. Well, this is going to require the multiplication rule. And what I want to point out, I wish Mubot was here today. We have a bot, Mubot. Oh, man. Mubot, you came back, and then you went away. Now we're all sad. Too bad.
I am sorry, Brian. You made a new picture of me and I don't like it.
Okay, chill out, Mubot. Chill out, chill out, chill out. Okay, let's go get the review, test 2. Ah, no, he's offended by it. That's what I get for making a new Mubot. The reason we're going to review test 2 is because we're going to look at the review sheet on here. And I'll drop this in the chat, so if you're watching this in the future, which I hope you do, you can go to review test 2, and review test 2 has the formula sheet. And on the formula sheet, when it loaded yesterday. Really? Why would something load yesterday and not today? Mubot, I think, is messing with us. Did I download it yesterday? I don't know if I downloaded it. That's great. Hey, formula sheet. So here we go. What you'll see right here is something huge to help you out with the test. You cannot bring notes to the test, but you can bring the formula sheet. What you'll see right here is the multiplication rule requires that two things are independent, and you use the word and. So with this question, Noel, if we are saying, what's the probability you get a lemon, which a lemon has a probability of 3 out of 10, and then you get a cherry, which has a probability of 2 out of 10, and we're getting it from up here. That's where we're doing it. And then you get a bell, which has a probability of 1 out of 10. What is the probability of getting a lemon and then a cherry and then a bell? And if you listen to my words there, I said a lemon and then a cherry and then a bell. And each time you spin the wheels are independent. The first wheel is not going to control what the second wheel gets. So what's the probability you get a lemon and then a cherry and then a bell? Each wheel is independent of the previous wheel when it spins. So what's the probability of a lemon and then a cherry and then a bell? That guy has or person has a Charmander profile. How did I not even see that Charmander right there? You're still watching. That's awesome. Kind of. So this is the probability of lemon. This is the probability of cherry. And this is the probability of bell. Remember, A and B are just placeholders for what you have right there. Like A and B are just placeholders. So what should you do with the probability? Go ahead and try it. What do you think you should do with the probability of a lemon and then a cherry and then a bell? Notice I'm saying and is just an alias for multiply. Well, double check. Yeah, double check your math. Double check your math. Put it in the calculator. Double check the math. You're on the right track, Noel. Double check your math though. So double check the math and tell me what you get. So Noel is doing the right thing, multiplying them together, a lemon, and then because the multiply is just an alias for and they have to be independent, which each wheel is, because when you spin the machine, the wheels don't control what the other wheels do. Each wheel is spinning independently of the previous wheel. So what do you get for this probability here? Double check the math. Good work. A lemon and then a cherry and then a bell. So you got to multiply them because we can multiply independent events to find out the probability they occur at the same time. Multiplication can be used when events are independent to find out the probability they occur at the same time. So the probability, if you multiply the bottom, you get 10 times 10 times 10, which is 1,000. And the top of it is 6, which is equal to 0.0006. I didn't add too many zeros, did I? 6 thousandths exactly. And I think I added one too many zeros. It is one too many zeros. I have added one too many zeros on this. It's interesting. I just noticed you can take the zeros here and align them like that. That is 6 thousandths right there. And correct me if I'm wrong. Someone's like, you didn't know that? You teach math? I'm like, well, it's interesting. Didn't notice that kind of has that relationship. I mean, it's going to either be one off. Everyone, decimals, like when you think of thousands and hundreds, like this is the tenths, this is the hundredths, this is the thousandths. So I guess, yeah, that makes sense too, because we have 6,000s. Yeah, multiplying the bottom's key. Yep. This one right here stops people, like bus stops. It's about bus stops. This one is very tough, but you can solve it very quickly. Your numbers are probably going to be different. So it says, for the next 4 stops, what is the probability the bus is on time for at least one stop? So the probability the bus arrives on time is 0.52. And I think we don't have it that it rounds. Oh, did they get me on the rounding? Ridiculous. We shouldn't have had a round in that. I didn't round it. So you do need to round it. Do round it. There should have been a plus or minus. We usually have plus or minuses on these. So if you were to get this, please contact me if you got that wrong. But I got the answer right there. But how in the world did I do that? This question for a lot of people has people stuck. They have no idea. They say, what in the world exactly, Noel? They're like, how did you calculate that? So here's how we do it. Let's first write out the sample space. What can happen with the bus? What's the 2 possible outcomes with the bus? What are the 2 possible outcomes with the bus? What are the 2 possible outcomes with the bus? What are the 2 possible outcomes with the bus? And what are their associated probabilities? Arriving on time, and late. So the bus either arrives on time or late. So probability on time, probability late. So now we have the probability of on time is 0.52, and the probability of late is 0.48, and these are complements. So we've already just used the complement rule. We can also see that the sample space adds up to 1, and we actually have just covered 3 rules of probability. First rule of probability is all probabilities are contained between 0 and 1. So if you look here at the first rule of probability, it meets it that every probability must be contained between 0 and 1, where 0 is never occurs and 1 is must occur. And the second rule of probability is the sample space adds up to 1, which we've done right here by listing out the sample space of everything that could occur. So the sample space is this. We could write the probability of the sample space, or the sample space is this right here. That is everything that could occur. We call it probability of sample space, and it must add up to 1. And we see the complement rule that if you do 1 minus an event, you get the things that do not occur. On the number 4, which on number 4? Question 4 that we did? Well, this one, oh, no, but we're not done. This is not the end of this question. So with this right here, it's with this question, this is just the start of it. Because the first thing you'd want to do is mark the information you have. Because this is a tough question. Exactly. So here's the thing it asks, and great answers, Noel, right there. What is the probability the bus is on time for at least 1 stop? So if you list out what could happen, we could have the bus be on time. We'll do an O as on time. It could be on time, late, on time, late, on time, late, on time. You know what's very interesting about this? If you think about this, this is a lot like our coin data set that we have, our coin sample space, where if we think about the bus being on time, we could just look at it like it's a heads. Does that make sense visually, Noel? Like when you think about the bus being on time or late, it's one of these 2 outcomes. Now, it's not 50-50, but if you think about on time or late, it looks like this, where the permutations of it, like the combinations of it, would be it's on time, late, on time, late, and these are all the things. But this is only where, and you see, it's kind of close to that answer. It's a little bit close to that. But the problem is the coins are 50-50. The coins are 50-50, and so the coins can be used where you do 1/16. So you're on the right track-ish. But let me ask you this. If we think of this occurrence right here as on time, let's say this is, because we're asking what's the probability that the bus is on time for at least 1 stop. Let's say this is equal to late. So heads means on time. Heads is on time. Does that make sense? If you see a heads, The bus was on time. How many times was the bus on time in this simulation? How many times was the bus on time in that simulation? How many times was it on time via that visual? 3. So now what we need to think is right here in all of these, the bus was on time at least once. So the bus is either late every time or on time at least once. So watch what I'm about to write right here, which is the key to this. The bus is either always late or on time. I'll make this bigger. At least once. I'm going to call this section of the video at least one problems because a lot of people get stuck on these. So okay. So does this make sense, Noel, that visually speaking, I want to get this on the same page maybe. The bus is either always late or it's on time at least once. Because here's the bus always late, and here's it on time at least once. So the bus will be it will either be always late or on time at least once. Does that make sense? So the bus is either always late or it's on time at least once. So since this is everything that can occur, what's the probability of this? This is everything that can occur because it's either going to be always late or on time at least once. What's the probability of this? It's the only 2 options, and one of them must occur. So this is the sample space of everything that could occur. So what's the probability of it? If we say it's either on time, not 50-50. So think of it, this is everything that could occur. The sample space has a probability of what? The sample space has a probability of what? The sample space has a probability of what? If you say, well, it's either going to be on time, it's either going to be exactly, it has a probability of 1. Because this is everything that could occur, so we could just say this right here. And we could even put some P's before for probability of always late or probability of on time at least once. So now, or is another way to say what? If I'm saying or, that's another way to what things together. By saying or, it's another way to what things together, which you see the answers on the screen. By saying or, to add them together. And also they have to be disjoint, which means they can't occur at the same time. Can the bus be late every time and on time at least once? No, they don't overlap. If it's late every time, it can't be on time at least once in these occurrences. So they are disjoint, which means they can't occur at the same time. So we change this to here. And wait a minute. We want to find out the probability the bus is on time at least once. Can't we just do some algebra? And what you do right here is you just take this and you subtract it from this side right here. It would subtract from both sides algebraically. And now look, this is what we're interested in finding. We're interested in the probability of on time at least once, and all we have to do is do 1 minus the probability of always late. So how do we figure out the probability of the bus being always late? Well, it was late at the first stop, and late at the second stop, and late at the third stop, and late at the fourth stop. When you hear me say and, we would what these together. When you hear me say and, we would what these together. When I say and, it's late at the first stop, late at the second stop, and late, not minus, good guess. If you hear me say and, it's late at the first stop and late at the second stop, you'd multiply. So you would say, well, what's the probability of it being probability of late and probability of late and probability of late and probability of late? And this would equal to 0.48 to the 4th power, because it's 0.48 times 0.48 times 0.48. And you go down here and you substitute this in. You do 1 minus 0.48 to the 4th power. Oh, not that. There we go. And that is going to equal to about 0.9467 or something. We found that out a moment ago. And there it is right there, 947. There it is. So that is how we solve it. These questions destroy people. I'll go to chapter 12. I'll do another one of it. When you know how to solve these, they get really easy. So I'm hoping people watch this section of the video, because people get to these test questions, they say, I have no idea how to solve it. They say, I've got no idea. For a sales promotion, the manufacturer says places winning symbols under 27% of the caps. What's the probability you win something if you buy a 6-pack? 2, 3, 4, 5, 6. There we go. It's because I know how to do it, because I've done a lot of these. Let's look at this question right here and mark example 2, at least one problem, example 2. So let's show how to do this because people have no idea how to do this on the test. Stat 201, chapter 12, at least one problems, example 2. I love these questions. I love the math. Math is where it's at. So when you look at this question, you have to think about it theoretically again. Noel, if you bought a 6-pack of soda, I love some soda. What would you want to happen with winning soda caps? What would you want to happen with the winning soda caps? What would you want to happen with the winning soda caps? So you got a 6-pack of soda and you open it up and you look under the cap. You'd love to win everything, right? Win on all 6. So win on every single soda. What's the probability you win and win and win and win 6 times in a row? Be very careful. Remember, there's the multiplication rule, and each soda is independent of the previous soda on whether you win, which means winning on the first soda does not change the probability of winning on the second. So what's the probability you win on the first soda and the second soda and the third soda and the fourth soda? What's the probability you win and you win and you win and you win? What would be the probability of winning on 6 sodas in a row? What is the probability of winning on 6 sodas in a row? I'll help you out a little bit here as we work on this. The probability of win is equal to 27%. The probability of lose or not win, we'll call it not win, is equal to 73%. So what's the probability you win on the first and win on the second and win on the third and win on the fourth and win on the fifth and win on the sixth? It's probability you win on all 6 sodas. What's probably you win and you win and you win and you win and you're just like, yes, I won so much soda. You win and you win and you win and you win. What's the probability of that? I thought I saw me bot. Well, that's the probability of 1 soda. The probability of winning on 1 soda is 27%. So what's the probability of winning? 27%. What's the probability of winning twice? Like you win on the first soda and you win on the second soda. So what's the probability of winning on the first soda and then winning on the second soda? Like in a row. Like you're like, let me see if I win on 2 sodas in a row. Yeah, I won. Hey, what's up, Evan? Good to see you. If you got questions, let me know. Got some lab today coming up. I didn't bring my computer. What's probably you win on the first and win on the second? What's probably you win on the first and win on the second? Well, we wouldn't add them because we only add disjoint events. And you could win on the first and win on the second, meaning they're not disjoint. The way to just check disjoint, which is when we can add things together to say this occurs or this occurs. And always look at the keywords. You'll hear me say if I say or, we're talking about adding. And you need to check that things are disjoint. Any case, how to set the code for assignment? We might need to do that during, maybe, we got 20 more minutes? Yeah, we can do that next year. You got it, Evan. I don't want to do all of it, but I'll show you some hints here. Let's do that next. You got it. So if we were saying, and Evan, help us out if you want to do some probability review, what's the probability you win on the first soda, which it has a 27% probability, and then win on the second soda? And we'll do that next, Evan. What's the probability you win on the first soda and then win on the next soda? What's the probability you win on the first soda and then win on the next soda? The probability you win on the first soda and then win on the next soda. Any ideas? So the first soda has a probability of 27%. That's right, Noel. So when you think about things occurring in sequence, the probability you win on the first is 27%, and then the next is 27%, and the third. So if winning on 6 sodas in a row would have a probability, what? Great job, Noel. That's what I wanted you to get to. So the probability of winning on 6 sodas in a row has a probability of what? The probability of winning on 6 sodas in a row has a probability of what? The probability of winning on 6 sodas in a row has a probability of what? Like winning on the first and the second and the third and the fourth and the fifth and the sixth? To win on 6 sodas, which is very unlikely. What's the probability? It would be super duper unlikely to win on 6 sodas in a row. So what's the probability you win on all 6 in a row? You're like, man, I won on the first and the second and the third. And you see, I keep saying and means multiply. So what's the probability of winning on the first and the second and the third and the fourth and the fifth and the sixth soda? What's the probability of all that? So on the first and the second and the third and the fourth and the fifth and the sixth. Evan, I think, has it. We're going to multiply. We're going to raise to 6 power. So 2, 3, 4, 5, 6. There we go right there. And nice job, Noah and Evan. Good work. I wish Meatball was here to give some points. It is Wacky Wednesdays. So with this, as we get Crash in here, I got to hit the Wacky Wednesdays sometimes. We're... Away, Crash. Wacky Wednesdays. Explosion. With this in mind, we are not doing the probability of winning on 6 in a row because we want to find the probability of win something. Well, we will either win something or the probability we will win nothing. So we will either win something or nothing because it asks what's the probability you win at least once. And one of these things must occur. You will either win something or nothing. And you could win like 2 prizes. That's winning something. You could win 1 prize. That's winning something. Winning nothing would be whatting? It would be losing 6 times in a row. So when we say winning nothing, well, we could just rewrite that as the probability of losing 6 times in a row. So probability of lose 6 times in a row. And well, now that we've rewrote that as the probability of winning or losing, 6 times in a row, we can just say, well, the probability of losing 6 times in a row, oops, is that. And then you just solve. You just algebra it. You go here and you subtract from both sides. Teachers got mad at me for not showing my work all the time in school. Now I just have to show it to teach it. But there you go right there. That's going to solve to the probability that we got for the answer of like 83% or something. So 0.73, 2, 3, 4, 5, 6, and then 1 minus, and there's the answer right there. The better you get at these, the more you can kind of see the answers to them. There's a light bulb one too. Here's the light bulb one. What's probably at least one of your light bulbs is defective. So either they're all going to work, and there's a 5-pack, I think. It's a 5-pack. So 2, 3, 4, 5. Either all going to work. I think I did it right. At least one defective. So either they all work or they're at least one defective. So I think I did it. Sometimes you can reverse it. There we go. And so it really, I've done a lot of these, and then I just think to myself, well, either they all work or they're at least one defective. So 1 minus the probability of all work. See how I say like 1 equals all work or at least one defective. So 1 minus. The 73, where did the 73 come from? Good question, Noel. Where did the first thing I do when I'm doing these the long way, which I do them the long way when teaching, is I always write out, what is this called? Think of SS. This is called, or yes, this is called. What is this? What did I write right here? And good answer is Evan 2. That is called the what right there. Evan's shown the math, and that is called the what of what could occur. We call that the what. What is that called? Not winning, exactly. We call that thing the what. So I always write that to begin. So whenever I'm doing a question like that, if I'm doing the big steps, I'm not just doing it really fast, I'm always going to write my sample space of everything that could occur. So when you get a soda, either you win or you do not win. And then I have right here, winning nothing would be, and this is losing. We could rewrite it to losing, because if you did not win, you lost. And then you could also say, well, we could have called this right here, not win 6 times. So winning nothing means you did not win 6 times. And that might make more sense right here. Probability of not win 6 times, which is 0.73 times 0.73 times 0.73, which is abbreviated to this. So really good stuff right there. Let's do some R code, Hackerman. Probably still on the screen behind me now. I need to play the music. We haven't done Hackerman lately. Where's my Hackerman? I don't think the music plays on this. Hey, let's do some R code. Studio, my favorite time of the day when we do some R code, but Meebot's not here to do R code with us. I'm gonna try to log in on the UT computers and get my Kahoot going. We'll see if it works. Either way, I'm doing lurking variables coming up here soon. We're doing lurking variables in 474, 479. Oh my gosh. Okay, let's go do this. I am going to not use ChatGPT. I think I have, do I have it on this computer, NFL FastR? I do. NFL plot R? What is that? A set of functions to visualize National Football League analysis in ggplot2, NFL R Reader, a minimum package for downloading data from GitHub repository from the NFL universe. So NFL Fast R, we're going to go to load player stats. I got to mark this in the video so people can come back. And thank you, Evan, for being here and asking this. Hopefully this helps a lot of students because I could see how people get stuck on this. Oh, this is not set to a 1. This is BS 320. And we have loading data from NFL Fast R. Okay. So we're going to load player stats. There's a lot of different ways to do this, but you can just go 2019 through 2023. But there's a problem, is I didn't save it. So what do I need to do and put before this, Evan? Yeah, thank you, Evan. What should I put before this to save this object? To save it into an object, rather. What should I do before this to save this into an object? What should I do? We want to save into something. Like we save models. We save models into M. We save models into M. You can save anything as anything. You can just call a name inside of code and save it. Yeah, exactly. Well, not model. Because we don't need to call whatever we put here. No, it's fine. It's practice. It's practice. It's like playing a scale. You become quicker each time you play it, and it's more fluid. You got it partially right. We'll throw you some Mewbox points, but Mewbot's not here to give them out, but you still get the nice graphic on the screen. But you're right that you do left arrow. So you basically had it. You were very close. And so then you could always ask ChatGPT like what I do wrong, and explain to me what this is. That means assign to or store into. So if you notice, this creates output right here. But then instead of it just printing to the screen, now when I run it, it won't print to the screen, it'll create the object. So you can see the object being created in the global environment in the top right corner over there. So now we need to look at this. The first thing you want to do usually, and I don't think Glimpse is loaded up, people go too quickly through stuff, especially, I'm trying to use less, it's not Glimpse, I'm dplyr library. People go too quickly sometimes and they don't do the steps that an analyst would do because they're like, ChatGPT will do it all. And I'm guilty of that. So here we are with the data. There are some issues here. We do have characters where we should probably have factors. Like a lot of these could be factors. We have headshot URL, which is kind of nice. You can do a lot of cool stuff with this. I'm not going to do it right now, but man, I just had cool ideas. I was like, oh man, you can do so many fun things. And you've got the team they were on for that season, and then you've got the season, all this good stuff. And actually, I've done this code on ChatGPT so much that I've learned how to do it. And it's not that difficult. What we want to do right now, and let me see if it works, is we want to take the NFL data set, and we're going to do a pipe. Now, you have to have dplyr on to do a pipe, because pipes are inside of dplyr. They use pipes. It's just going to pass it off to the next thing, and we're going to say group by. So when I say group by, it's going to group together everything within that group. So let's go right here and say group by, let's go to player name, and it's going to autocomplete to player name, and let's go to season. And we might have just done it. Okay, let's say by season. And I don't know. Let me see right here. Doesn't look right to me yet. Okay. No, that's not it. Oh, Brian got it wrong. Maybe it's season first. It might be season first. Might matter how you group by. Ooh, it didn't do it either. Okay. Is it not group by? We should group by season. What? Maybe. I've done it so many times with ChatGPT, it's not fair. That's good. Nice. Good, 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 good. Okay. There we go. Now we've done it. So you need a summarization right there. And that's taking... So think about what I've done, Evan. What have I created right here? You can see what I've created. And what have I created? What have I created? We've used no ChatGPT. What have I created? What do these numbers mean? What's this number? What is this? What does any of this mean? What have I done? What have I done? What do we have? P. Mahomes? Patrick Mahomes. It's sad I've learned enough football to know a lot of the names. I don't know that name. Had a good season, though. Someone's like, you don't know Jeffrey Winston? Everyone knows Tom Brady. I was thinking Drew Brees. Patrick Mahomes. In Jeopardy format, what is a table of passing yards? It's the sum, exactly. So it's each season, and it has the season, and it has by player. So if you look, we grouped by the season and the player. So that's what we got right there, is like it's separated by season, separated by player. And then this right here is the key, is that we summarized and made a new variable called passing yards total. And you see it's called passing yards total right there for the season. What you can do right here is you can add another variable, and please don't do exactly what I'm doing right here. Please don't do this. I think one or two, please, every report, don't do this. You can just do another. I'm afraid everyone's going to do exactly what I do. Be like, oh, I'm going to look at just this. So you could go to air yards. What is that? Go to running yards total. What is it? It's not called running yards? Passing and what are the receiving yards? What are receiving yards? Where's my autocomplete? There we go. Receiving yards equals sum of, and then receiving, oh wait, we're going to call it total. Total. And now we have this, and there it is right there. And you notice, because they're quarterbacks, you're going to see an inverse relationship here. And that's kind of interesting. So now we can go and make a model and just do the receiving yards explained by passing yards. And data equals by season. And then visualize. Oh, no reg class. How are you able to see the table? To see the table, go over here and click on by season, and then you can view it. So you can open it up with the blue arrow to see what's going on. Zero tables. Oh, yeah, let me know if you can't see it or what's going on. But to view a table, you simply go inside of here and click it, and that does the view function down there, and you're just looking at like an Excel spreadsheet, so you can see what's going on. You can also look at the variables inside of here to see what's going on. It's got some attributes, which are like additional things that it learned about the data, or it has in the table to let me know. And I just didn't see my by season. Yep. And don't do exactly what I'm doing. Please don't do exactly. I want to see unique reports, because one, you need the output to look good. So remember, everything we turn in, we want to look nice. Like if you turn in this graphic, I'm hoping Meath is given some very low grades. This is, you can make it look a little bit better, but also we're going to try to use ggplots and everything to make graphics look good, and you shouldn't be using the default output. Also, this on a check regression is going to have the craziest of problems. Exactly. This, I hope no one makes this model, because my gosh, this model is garbage. Wow. Yeah, everything's zero. Or what? Linearity passes? Oh, I don't even know how linearity is passing. Equal spread doesn't pass. Why in the world is linearity going to pass? That is a shocker to me. I have no idea how linearity passes. Apparently it does. I think maybe the test is just not set up to do. That's so weird. I'll tell you, that's a non-linear relationship if I ever saw one. But it's because all the bulk of the data is in there. It's got to be because of it. And the reason you're seeing this is because quarterbacks have a whole different pattern than wide, like non-quarterbacks. So I wonder if we can just easily go in here and say filter and position does not equal QB. Oh, I see we got someone else in here. Who are these people with their zeros? And then let's add another filter. Passing yards equals 0, 0. Okay, so filter. Passing yards does not equal 0. Filter. Running yards. Really? Receiving yards. No. Receiving. Oh, no. We gotta. We're gonna run into a problem on this because that's gonna take away rows with individuals. It has to be after we've summarized. It has to be after the summarization. After the summarization of the data, we're gonna have to filter. If you were doing this, because don't do exactly what I'm doing, but this is how you kind of examine data, is you say, okay, now passing yards total not equal to 0. People who have some passing yards in the NFL, let's look at their relationship to filter. We could do running yards and reception yards, and there's all different things you can do. And so now we've got receiving yards total does not equal 0. There we go. This model almost passes. Passes everything but normality of residuals, which truthfully doesn't look that bad. I would let this pass, normality of residuals. The model's a lot weaker. But there is a positive linear relationship. And I'd be interested, especially that person up there that's an outlier, like what happened with them that they got so many receiving yards. And it's interesting. What's going on? You got a big outlier down there at the end of it. And this is a very small subset of players. Let's go to the by season data set, look at some of the names. People might know them by season. Now we only have 72 players that have some passing and receiving yards. And there's the list of the players. It must be, you look at their receiving yards are a lot higher. And it must be people who, it's interesting. It tells you something maybe about like these players that do a quarterback type pass situation. C. Wilson. Who is that? Is Caleb Wilson. Might be really good. He's English. Wait. I'm so confused. He's a soccer player. He's soccer. Football. That's weird. Cedric Wilson. I've heard of Cedric Wilson. 28. Cedric Wilson. Do you have a father who played? Look, he did. May have just heard of him in the yeah, like, so Cedric Wilson Jr. Oh no, he doesn't have Jr. on his name. He's a wide receiver. Interesting. Why does he have passing yards? He must have passed for a touchdown. He's not good. Why does he have passing yards though? So did he try to QB? Did he try to QB? 14 yards per carry? Interesting. So he's got passing stats. And I wonder what's going on outside. Says he has passing yards, unless I've got the wrong one. See, he might not even passing. Yeah, it says he has 74 passing yards, right? And that's what we see in our data set. I don't know. It just creates a lot of questions. He's 88. Really? Yeah, and it's interesting to think. And the relationship you see right here for these are non-quarterbacks who have passing and receiving yards. And there is a positive linear relationship that people who are better at passing, like we would expect them, like between two individuals. I don't know. I have to look more at the data. But you do have the big outlier here at the end who has really just failed at it. But for two individuals who differ in their passing yards by 1, we'd expect them to have a higher receiving yards. So it might speak to the idea that we should maybe reverse this, that if someone's receiving the ball, how would that explain them throwing the ball? I gotta head off to class here in a moment. But kind of this investigation, does that make sense? We're investigating, Evan? Like, is there a relationship between people who can receive the ball that would predict if they can throw the ball? And frankly, here's the thing. What I've learned from this is that there is a relationship that people who can receive the ball, those individuals, you take two people and someone who's better at receiving is better at passing the ball too. And there's a statistically significant relationship between people who can receive the ball. It's a very limited data set and the p-value is barely below 0.05, but there is a statistically significant relationship. It's not that strong of a relationship, but I'd say, and we'd also want to investigate that outlier over there. Who's the max? Let me go look at them. That's the last thing I'll do. We could just look for passing yards of max passing yards. Okay, so that person is a huge outlier, and we'll end with that. These are the things I go through. So the max passing yards. It's that person, right? Wait, is that them? Oh, so they're not that good, you're saying? Yeah, it's them. Okay. Well, they're a huge outlier because, and their receiving yards. No, that's not the right person. Oh, because Petrie's thing doesn't. That right there is Jay Landry, because Petrie's thing doesn't always show all the data. He was at Dallas in 2021. Dak Prescott caught one of his. Well, he would have had a thrown for Dak Prescott. So, is Jarvis Landry good? Let me ask you this: I would say, from what I'm saying, I want to check out more. I would, from this model, with my limited knowledge of football, I'd say I think Jarvis Landry is pretty darn good. I think Jarvis Landry has a lot of skills. I think Jarvis Landry might not be utilized enough. So what I'm seeing right here is Jarvis Landry. I'm saying something going on that we need to be like, this guy's pretty good. He's the most popular player through the first 6 seasons. Yeah, it is. Look at this. So Jarvis Landry, what do you think, Evan? With my limited knowledge, I'm calling Jarvis Landry an outlier right there and somebody worth noting. And that's what my analysis showed, that he's way above what we would expect when he's done these things. So I would say he's being underutilized. He's well above. Yeah. So that's, and C. Wilson, actually, he's way above too. Yeah, we don't see. So let me go look at the residual plot on this. I got too many things. We want to go look at influential plot. Oh, no one's influential. Look at that. Well, no one's influential. We do have those points up there I want to examine further, but yeah. So these ones over here. Oh, yeah, T. Kennedy. Out of C. Wilson, out of examined, and Jay Landry out of examined. Maybe T. Kennedy too. I want to know what happened here. They're near the bottom of the model. But I might just have to plot it by basic plotting to see them. So I have too much fun looking at data. So we know you got a problem. Make sure your plots look pretty. I have not worked on any pretty plots right here. So you are not seeing pretty plots. You're seeing very basic plots. These are not plots I would turn in for a report. There's our 3 right there. These 3 points. So I would go through ggplots and try to illustrate. Really what you're looking at here is you've got these 3 data points right there. And this was the one we were examining just a moment ago. There's the first guy and there's another guy. So those 3 right there are things that definitely break away from the rest of the model and are somewhat influential points. But I would examine those. Does that make sense, Evan? Like, please don't do the exact same analysis I've done everyone in 320, but this is where you want to make your report look pretty, and this is the simple linear regression. And so in the 30 minutes or so, I've done an examination, I've looked into players that don't follow the trend, I've talked about the trend that is statistically significant, I've checked the models, I know things that you might not know, like filtering, but any question you have on how to do this, we can find a way. You just analyze data. You see what you see. You might see something cool. You might find something. With that, it's time to end class or end office hours. Evan, great questions. Bye for now, everyone. Bye. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.